The final topic that we're going to cover in this course is the idea of angular momentum. Like the other linear quantities that we learned have a rotational analog, momentum itself also possesses a rotational analog known as angular momentum. Angular momentum is designated by the letter capital L, and angular momentum could be thought of as the tendency of an object to maintain its rate of rotation. Think about this description in the context of how we described linear momentum, p, as the tendency of an object to maintain its velocity. Now, if an object is moving through space with some velocity, it will possess some amount of momentum. And if you want that object's momentum to change, if you want to change the object's velocity, then you need to push on the object. In other words, you need to apply an external force to the object to change its momentum. Similarly, if an object is spinning, that object will have some non-zero angular momentum. And if you want that object's angular momentum to change, then you need to apply an external torque to the object. Torque, as we said, is the rotational analog to force. The equation for the angular momentum of a single rotating object is L equals I omega. In this equation, I is the moment of inertia of that rotating object. We said previously that you could think of moment of inertia as the rotational analog to mass, and omega is that object's angular velocity. In other words, that object's rate of spin. And you could think of angular velocity as the rotational analog to linear velocity. Notice the very strong resemblance between the equation for the angular momentum of a rotating object and the equation for linear momentum of a moving object that we discussed in the previous chapter. Like linear momentum, angular momentum is a conserved quantity. That means that if I have a system of multiple objects and those objects are all spinning, then I could say each of those objects possesses some amount of angular momentum at any given moment. And if those objects are to interact with each other in some manner, the total amount of angular momentum before the interaction must be equal to the total amount of angular momentum after the interaction. I could expand this idea out by writing I1 initial, omega 1 initial, plus I2 initial, omega 2 initial, on and on, equals I1 final, omega 1 final, plus I2 final, omega 2 final, on and on. The angular momentum of individual objects is allowed to change, but the total angular momentum of every object in that system must be unchanged from before an interaction to after an interaction. Notice how the line above looks very similar to the way we wrote out the conservation of linear momentum in 1D. And finally, one significant difference between the conservation of linear momentum problems that we have considered and the conservation of angular momentum that we will shortly see is that when we deal with conservation of angular momentum, we will encounter scenarios where the moment of inertia of an object changes. So that means we will have a notion of I1 initial and I1 final. When we dealt with the conservation of linear momentum, the mass of the particles in our system never changed, so I did not need to differentiate between M1 final and M1 initial. However, if an object somehow changes its shape, so you could imagine maybe an object collapses on itself or balloons up or somehow otherwise changes its shape, then that means the atoms have rearranged themselves. Some of them might be closer to or further away from the center of rotation, and that would imply the moment of inertia has changed. So when we deal with the conservation of angular momentum, in addition to tracking the initial and final angular velocities of all the objects in my system, I will need to often track the initial and final moment of inertia of all the objects in my system. In this example problem, we are told there's a dog sitting near the outer edge of a merry-go-round. The merry-go-round is spinning around at a rate of 5 radians per second. So I could phrase that as the merry-go-round has an angular velocity of 5 radians per second with the dog riding around on it. So I could write omega initial is equal to 5 radians per second. We are told if the dog decides it wants to get up, move towards the center of the merry-go-round, what will the merry-go-round's new rate of rotation be with the dog sitting near the center? So that's essentially asking what is omega final equal to? To answer this question, we are going to use the idea of the conservation of angular momentum. Back in chapter 7, we learned about linear momentum. Linear momentum is described by the equation P equals mv, and momentum is a vector quantity, direction matters. The idea of conservation of momentum is basically saying if we have a system of particles and all those particles interact in some way, they might be colliding or fusing together or exploding or doing something else. No matter what happens in that system, I know momentum will always be a conserved quantity. So the total momentum of every particle before the interaction is going to equal the total momentum of every particle after the interaction. I could write that as an equation by writing P total initial equals P total final. And when I write total, I'm essentially saying the sum of the momentum of every object in my system. In this particular system, we have two objects. We have a dog and a merry-go-round. The rotational analog of momentum, which is angular momentum, is the rotational analog of mass times the rotational analog of velocity. The rotational analog of mass is moment of inertia, and the rotational analog of velocity is angular velocity. So I could write angular momentum, which is designated by capital letter L, as I times omega. Now, in this problem, there are some simplifications we can make. We have two objects. We have a dog and a merry-go-round. However, the angular velocity of the dog and the angular velocity of the merry-go-round are always going to be the same in this particular problem. In other problems, that might not always be the case. But the dog is always sitting on the merry-go-round like a good boy riding around. They always will be spinning at the same rate. Now, for the moment of inertia, I, we said that moment of inertia is the sum of mr squared of every atom that makes up our object. So I would write I total, in principle, is written as sum over mr squared. In this example, we do not know what the mass of the dog is. We don't know what the mass of the merry-go-round is, how big they are, but we don't need to know that. By looking at this picture and thinking about what happens, if I think of the moment of inertia as the sum of the mass of every atom times the distance from the center of rotation of every atom, I could very clearly see, just based on how this picture is drawn, there are more atoms further away from the center of rotation here at the initial moment compared to here when more atoms are closer to the center of rotation. That tells me that I expect r squared to be smaller for a lot of the atoms when we, in principle, calculate the sum. However, we don't even need to calculate the sum because we are given the total moment of inertia of everything in the system before the dog moves to the center of the merry-go-round and after the dog moves to the center of the merry-go-round. So we could just right away go ahead and calculate conservation of angular momentum and use that to find the final rotational velocity of the dog and the merry-go-round. So I could write this as L total initial equals L total final. Because the dog and the merry-go-round are spinning at the same rate, I could almost think of them as one single connected object. Just like when two figure skaters collide and move off together, you could think of them as one object since they have the same velocity. So I would say the initial moment of inertia of the dog plus the merry-go-round is 2.25. The initial angular velocity of the dog plus the merry-go-round is 5 radians per second. So I have a factor of 5 here. The final Moment of inertia for the dog in the merry-go-round is 1.8, and omega final is what we're trying to find. When I put these numbers in a calculator, I find the final rate of rotation for the dog on the merry-go-round is omega final equals 6.28 radians per second. In this example problem, we have a rod that falls onto a spinning disc. Initially, the rod is not spinning, and we're told that the disc is spinning at a rate of 7 revolutions per second. So here I drew a picture of the setup. We have the rod that is falling but initially not spinning, and the disc that is initially spinning. And we're told that after the rod hits the disc, the rod attaches or sticks to the disc, and the rod and the disc spin off together. Because they're spinning together, they will have the same final angular velocity, and we're asked to find what that final angular velocity is. So here's a picture of the two objects spinning as one. Now, we're not told what the mass of the rod and the disc are, but we're told they're the same mass. And we're also told that the length of the rod is equal to the diameter of the disc, even though we're not told what that length is. To answer that question, I'm going to use the idea of conservation of angular momentum. So angular momentum of a single object could be written as L equals I omega. Now, we'll need to know what is the moment of inertia, I, for the disc and the rod. So I'm going to go to a chart in the textbook and look up the moment of inertia of these two objects. And when I do, I find that for a disc of mass capital M and radius capital R, the moment of inertia of a disc is 1/2 mr squared. And the moment of inertia for a spinning rod of total length L and mass M is 1/12 ml squared. So now I could write out the conservation of angular momentum. The total angular momentum of every object before the collision is equal to the total angular momentum of every object in the system after the collision. Here I have two objects in my system. I have a disc and a rod. So I will add their angular momentums together. So I could write that as the angular momentum of the rod initial plus the angular momentum of the disc initial equals the angular momentum of the rod final plus the angular momentum of the disc final. Now we are going to write out each of the terms in the angular momentum of the disc and the rod. So I could write for the initial angular momentum of the rod, I rod times omega rod initial plus I disc omega disc initial, and then the final angular momentum of the disc and the rod will be I rod omega rod final plus I disc omega disc final. Before I go on and start solving this equation, let's look at what we really have here. We have a lot written on the board, but most of it is subscripts. I do want to differentiate between the rod and the disc and initial and final. But angular momentum only depends on two factors: the moment of inertia, which is the rotational analog to mass, and the angular velocity, which is the rotational analog to velocity. If I, instead of labeling these objects as rod and disc, if I label them as object 1 and object 2, notice that everything I have written on the board here strongly resembles M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. The conservation of angular momentum is the rotational analog of the conservation of linear momentum that we've already worked with a lot in this course. Another thing I want to take a moment to point out before I go ahead and solve. When we worked with the conservation of linear momentum, The mass of the particles that were interacting in some manner never changed. The mass of particle 1 never changed before the collision versus after, so we did not need to specify M1 initial versus M1 final. It was always the same mass. When you are looking at conservation of angular momentum in this chapter, it is possible for the rotational analog of mass. It is possible for moment of inertia to change before something happens versus after. We saw that very explicitly in the previous example. There was a dog on the outer edge of a merry-go-round and they were spinning around. They had some moment of inertia, and then the dog moved closer to the center of rotation, and the object that was spinning changed its moment of inertia. When an object changes its shape in some manner, it might change its moment of inertia. That was not something we saw when we worked with conservation of linear momentum. Here, the masses of the objects that were interacting always stayed the same. They did not have initial versus final values. When we deal with conservation of angular momentum, we need to be aware of the possibility that moment of inertia might change before an interaction compared to after. It turns out in this problem that is not going to be the case. But in the previous example, that did happen, and I just wanted to point that out. So now we could go ahead and solve for the final angular velocity of the disk and the rod, and we could start plugging in some numbers to simplify this equation. We are told that initially the rod is not spinning at all. So that means this omega rod initial is going to be equal to 0. We are also told that the rod and the disk have the same final angular velocity. So this term here, omega rod final and omega disk final, will be the same. So I'll just call them omega final just so I don't have to write as many subscripts. So let's write out what we have. We have the moment of inertia of the disk is 1/2 mr squared. And the initial angular velocity of the disk, we're told, is 7 revolutions per second. If I wanted, I could convert to radians per second. In most problems, I do that, but in this problem, I don't feel like doing it, so I'm not going to. So I'll have that times 7. I didn't bother with this term because it's multiplied by 0 anyway. And then I could write equals the moment of inertia of the rod, 1/12 ml squared, times the final angular velocity of the rod, omega final, plus the moment of inertia of the disk, 1/2 mr squared, times the final angular velocity of the disk. I did not bother differentiating between the final angular velocity of the disk versus the final angular velocity of the rod because, as we said, they are spinning together. Now let's see what we have here. I got rid of this term because I'm multiplying by 0 anyway. We were not given the mass of the disk or the rod, but it turns out that's okay because I notice the mass is everywhere in this problem, so I could divide the mass out anyway. So I could get rid of the masses right away. And when I do that, I would get one-half times r squared times 7 equals 1/12 times L squared omega final plus 1/2 r squared times omega final. Now I have omega final in both terms on the right-hand side, so I could combine the terms on the right-hand side to be 1/12 L squared plus 1/2 r squared times omega final. Just to make my algebra a little bit easier, on the left-hand side, I'll just write this as 7/2 r squared. And what I'm going to do next is I'm going to think about the connection between L and R. In this problem, what we had is we have a rod of length L and a disc of radius R. But the length of the rod is the same as the diameter of the disc. So if I were to draw a picture of this, here is my disc, and this disc has a radius R, and the rod itself has a length equal to the diameter. So I could say the length of the rod is equal to 2 times R. So if I want, I could say, therefore, L is going to be replaced by 2R. So since L is equal to 2R, that implies L squared would be 4R squared. When I square the L, I have to square both the R and the 2. That gives me my factor of 4 here. So if I want, I could replace this L with a factor of 4R squared. And now when I do a little bit more algebra, I find 7 over 2 R squared is equal to 4 over 12 will give me 1/3 R squared plus 1/2 R squared. And then I have times omega final. And just like how the masses canceled out everywhere in this problem, the R squareds will cancel out everywhere in this problem. And now all I'm left with is omega final and a couple numbers that I need to combine. So if I want to combine these numbers, here I'll have 7 over 2 is equal to 1/3 and 1/2. So this is going to be 2 over 6 plus 3 over 6 times omega final. And when I combine these, 6 times 7 will give me 42. 5 times 2 will give me 10. So I'll get 42 over 10 is equal to omega final. And because the units of the angular velocity were written in revolutions per second, the final angular velocity is 42/10, which is equal to 4.2 revolutions per second for omega final.